Okay, so welcome back everyone. Today we're going to be looking at the reactions of benzene. Previously we've looked at the structure of benzene and we've looked at naming benzene compounds or naming aromatic compounds in previous videos. So, first question to ask in terms of reactions of benzene is what type of reactions does benzene undergo? In a previous video I've talked about the fact that benzene doesn't undergo addition reactions. So if I was to try and add bromine to this benzene ring, it wouldn't work. So there'd be no products being formed, the reaction wouldn't work. So addition reactions don't work, and the main reason why addition reactions don't work is that it would disturb this delocalized pi ring. So if I wanted to add bromines on, this pi ring would be disrupted. So instead, what benzene can do is undergo substitution reactions. So instead, this time we're going to try and do a substitution reaction where one of the bromine atoms is going to substitute in place of a hydrogen. So I'm going to end up with these as my products. So one of the bromines is substituted for the hydrogen, and then my side product is HBr. These are the types of reactions that benzene undergoes, and the reason it undergoes substitution rather than addition is that substitution reactions maintain this delocalized pi ring, so they don't disrupt it, and so benzene maintains its stability. So in this video we're going to look at 3 different substitution reactions that you can do with a benzene ring. So the first type of reaction that you can do with a benzene ring is you can convert benzene into nitrobenzene. So we can go from benzene looking like that, and we can convert it into nitrobenzene looking like this there. Okay, so we've done a substitution reaction. Now more specifically, this type of reaction is called an electrophilic substitution reaction. So it's an electrophilic substitution reaction. In order to do this conversion, so my conditions are that I'm going to need concentrated nitric acid and concentrated sulfuric acid, and then once I've added those I'm going to need to heat it up to 50 degrees Celsius. If I add those things to the benzene, this conversion will take place. Now this obviously isn't balanced, so if I wanted to balance it, I would have HNO3 reacting, and the side product here would be water. Okay, so we've got a substitution reaction happening where we're nitrating benzene. Now for all this, you need to know the mechanism for the reaction. So what on earth is the mechanism for this reaction? How does this take place in terms of the movement of electrons? Well, there's 3 parts to it. Part 1 is the formation of an electrophile by the catalyst. So if I show you the equation and then I'll explain it. So you've got the 2 acids which react together. We make this as a product, we make this as a product, and we make this as a product. So a sulfuric acid here is acting as a catalyst, and it is allowing us to form this, which is an electrophile. So that's the first step of my mechanism, is forming this as an electrophile here, which is then, so the type of mechanism is called electrophilic substitution. So this electrophile is going to be substituted into the benzene ring here. So once I've made my electrophile, second part of the reaction is substitution. So this is the key part. Substitution, where my electrophile gets substituted into my benzene ring. So here's my benzene ring. Here's my electrophile, NO2+. What will happen is the electrons in this delocalized ring will come out. I'm going to do it with a different color to make it a bit clearer. Will come out and attack this NO2+. So the arrow, the direction of the arrow and where it comes from and it goes to is important. So it needs to come from the delocalized ring and it needs to go and attack this NO2+ molecule. If it's coming from somewhere else and going to somewhere else, you're not going to get yourself the mark. So the electrons come out and attack this electrophile, which produces this, which is an intermediate product. Okay, and then NO2 and H. So now what's happened is the electrons in this delocalized ring have come out and attacked the NO2 molecule and made a bond with this electrophile. You've still got the hydrogen there because that hasn't gone anywhere yet. And now the intermediate has a positive charge, so it's unstable. It has a positive charge which needs to be solved at some point. So in the final step of this substitution process, what happens is the hydrogen, the electrons in the hydrogen, carbon to hydrogen bond here, go in, and you can think of it as attack that positive charge to stabilize the ring and restore our delocalized ring, and we end up with NO2 and H plus, like that. And then in your final step of your mechanism, what you need to do is this catalyst here needs to be regenerated. So a catalyst is something that doesn't get used up in the reaction, so that it's going to be regenerated. So this final part of the mechanism is the regeneration of the catalyst. So we need to make H2SO4 again. What we do is we use the H plus that we formed in step 2 of the mechanism. We also use the HSO4 minus that's been hanging around since step 1 of the mechanism, and those two combine to reform our catalyst, which is H2SO4. So this thing here is a catalyst. Okay, so if I just maybe run you through that mechanism one more time just to help you picture it and help you note the key points. So what are we doing? We're performing a substitution reaction to convert benzene into nitrobenzene. It's called an electrophilic substitution reaction. Electrophilic because an electrophile is used in the substitution process. Conditions: concentrated nitric acid and concentrated sulfuric acid. This bit acts as the catalyst at 50 degrees Celsius. In the first step, you've got the two acids that combine in order to make your electrophile. And you can see here that there's the HSO4 minus, which is used to regenerate the catalyst later. This electrophile then gets attacked by the benzene ring, or more specifically the delocalized electrons in the benzene ring, to make this unstable intermediate. The electrons between the carbon and the hydrogen go in and attack the the positive intermediate that you've got here to stabilize it, so that we get nitrobenzene and H+. The final step then is the regeneration of the catalyst. H+, which you can see that's where the H+ is coming from, and the HSO4-. These two then combine to regenerate our catalyst here. Now, that's probably the most complicated mechanism that you've seen, maybe on a similar standard to free radical substitution, but you'll be pleased to know the other two reactions of benzene are almost identical in terms of their mechanism. So let's have a look at the other two now. Okay, so in the second reaction, what we're going to do is we're going to convert benzene into halobenzene, so some sort of halogen onto the benzene ring. I'm going to do it in general terms, so I'm going to use X to represent a halogen, but it could be chlorine, so it could make chlorobenzene, it could make bromobenzene, any sort of halogen getting substituted on. So overall, what are we doing? Starting with benzene, and we're making a substitution reaction take place where a halogen gets substituted on. So X could be chlorine, it could be bromine, it could be iodine, it could be any halogen. The type of reaction takes place, same again. So electrophilic substitution. Conditions and reagents that we need to use in order to actually get this reaction to work. So we need a halogen, so it might be Cl2, it might be Br2, and then we need anhydrous, so that means in the absence of water, we don't want any water present, either an aluminium halide catalyst, so it could be AlCl3, or an iron halide catalyst, so FeCl3 for example, and this one is done at 25 degrees Celsius. So mechanism for this reaction, that is not a good M, let's try that again. Mechanism, the steps are all the same. So A is formation of an electrophile. So we take the halogen and we take the catalyst, which I'm going to use AlX3, I could have used FeX3, and what it's going to make is X plus, so maybe Cl plus, and AlX4 minus. So here is my catalyst, and this thing here is my electrophile, which again you can see has got that positive charge, which means it's electron deficient and is going to get attacked by all those electrons in that benzene ring. So second step, substitution. Got my benzene ring, here's my electrophile. The electrons in this delocalized ring come out and attack the electrophile, which gives me an unstable intermediate that looks like this. So you can see there, when I'm drawing the unstable intermediate, I'm not drawing a complete circle because it's been disrupted, and I'm also putting a positive charge in the middle to signify that it's lacking electrons. So the X has now formed a bond, and we've still got the hydrogen. And what happens in order to reform the delocalized ring is the electrons in this bond come in, attack that positive charge, so we get X and H plus. Now, you should be able to see the pattern that's emerging here in terms of the mechanisms. They're pretty much the same. You're just changing the reagents and catalysts that you're using. So final step is reforming this catalyst. So what's going to happen is the AlX4 minus that we formed previously and the H plus are going to combine. So these two are going to combine together to give us our catalyst. So as before, final step is regeneration of the catalyst. So it's making that aluminium halide catalyst again. So we use AlX4 minus, H plus, and that's going to reform our catalyst, and then a side product HX. So there's our catalyst, which has been restored. So if we just run through that one again, what are we doing? Converting benzene into a halobenzene, so it could be chlorobenzene. There's our overall conversion that we're interested in. Type of reaction, electrophilic substitution. Conditions and reagents, we need the halogen source, so X2. We need an anhydrous, so lacking water catalyst, something like one of these two. And then if we mix those together at 25 degrees Celsius, we'll get the reaction to happen. In the first step, we form an electrophile. So the catalyst reacts with the source of halogen to make us this electrophile with the positive charge. That then gets attacked by the benzene and the delocalized electrons in the benzene ring to make this intermediate, which is stabilized by the electrons in the carbon to hydrogen bond going in to attack it. We get our halobenzene and H+, and then we use these two things here to regenerate our catalyst, and there it is, our catalyst being regenerated. So those are two of the reactions. We got one more which follows an almost identical pattern, but I need to make it explicit. So in the final reaction, what you have is benzene being converted into an alkyl benzene. So it might be like methyl benzene or ethyl benzene or something like that. So what is going on here? So I'm going to represent it generically like this, where R is any sort of carbon chain, alkane chain coming off the benzene. So it could be 5 carbons coming off the benzene, it could be 2, 1, doesn't really matter. So type of reaction taking place, electrophilic substitution again. Conditions and reagents in order to perform this reaction are that you need some sort of halogenoalkane. So I'm going to say that as RCl. So it could be chloroethane, it could be chloropropane, some sort of halogenoalkane that looks like that. And same catalysts as for the last reaction, so anhydrous AlCl3, and a temperature, this time slightly lower again, 0 to 25 degrees Celsius. So, mechanism, what actually takes place? Well, you should know by now. First step is going to be formation of an electrophile. So what happens is, I'm going to pick an example of a halogenoalkane now. So I'm going to do CH3CH2Cl. So I got chloroethane. It's reacting with the catalyst, and what gets formed is an electrophile. So there's my electrophile, and AlCl4 minus. So once again, catalyst, making my electrophile with the positive charge again. Step 2, substitution. So here's my benzene ring, my electrophiles CH3, CH2 plus. I'm going to go and attack so that we get this unstable intermediate again with CH2CH3 attached, and the hydrogen. Should have drawn that in pink, but you'll forgive me. This goes in and attacks there. So to stabilize our intermediate, we then end up with this. So now we've got ethyl benzene formed and H+. And then in the final step, these two things here are going to help me regenerate my catalyst. So C, regeneration of the catalyst, regeneration of catalyst. So H plus AlCl4 minus goes to make AlCl3 and HCl, and there's the return of my catalyst. Hopefully you can see the patterns in those reactions. I picked chloroethane here, but I could have picked any length of carbon chain and that would substitute onto the benzene ring for me. So those are the reactions of benzene.